now last time we saw already that from the first derivative we can get information about the monotonic behavior of the original function. In particular, if the first derivative is larger than 0, then the original function must be increasing. If the derivative is smaller than 0, then the original function must be decreasing. And we saw that we can use this increasing-decreasing test in order to figure out which critical numbers are actually extremas and which not. So we have last time we have seen a test which is called the first derivative test. So maybe let's do one more example, a simple one. If you have given this function on the interval 0 to 2 pi, okay, so you are asked to find, okay, on which subintervals is the function increasing, on which subintervals is the function decreasing. And normally this will also give you the local extremas. So we first look at the derivative. Okay, so the derivative is minus 2 cosine of x times the sine of x, minus 2 cosine of x. So we can take out minus 2 cosine of x, and we have the 1 plus sine of x. Now, the next step is normally to find the zeros of the derivative, because that's where we have possible sign changes. So we see the cosine of x is equal to 0 if either x is equal to pi half or x is equal to 3 pi half. And the sine of x is equal to minus 1 at this point here. So we just get the same points. So what you see here are what we call the critical numbers, because the derivative of this function exists everywhere. So there are no points where the derivative does not exist, and the derivative is 0 for those two numbers here. So those are the critical numbers. Those are the possible candidates for extreme values. Now, if we look at the sign change, you see that if you look at this part here, this is always larger or equal than 0. So just the behavior of the cosine is important. So you see if x is between 0 and pi half, then negative, so the function is decreasing. Then if x is between pi half and 3 pi half, positive, so the function is increasing. And if x is between 3 pi half and 2 pi, then again negative, so the function is decreasing again. In our textbook, the author suggests to make a table. So that's actually what I have done. So if you have given those critical points, you see you have to consider the cases where x is smaller than pi half, where x is between pi half and 3 pi half, and x is between 3 pi half and 2 pi. Okay, so those are the ranges for x we are interested in. And normally in the textbook you can always find a table where the author writes down all those involved factors, so the function f of x. But here we can see it immediately. So here smaller than 0, here larger than 0, and here smaller than 0 again. Okay, so in particular we see that at pi half we have a local minimum, and at 3 pi half we have a local maximum. Okay, so this already tells us quite a lot about the shape of this graph. Okay, so you have here pi half, here pi, here 3 pi half, and here 2 pi. Okay, so we know first decreasing. You also see that if you plug in 0, you get 1. So we start at 1. Then, so roughly first decreasing. Then from here increasing. And then decreasing again. Okay, but of course, this information, this is just roughly. Of course, this information is not enough in order to clearly understand how the function behaves. Of course, I should also compute the values of the function at pi half and 3 pi half in order to understand, okay, how high is this value and how high is this value. But what I'm still missing is I do not know whether at the beginning, so it could be that at the beginning here, from here to here, it could be that the function does not look actually like this here, but maybe the function look like this here. Also, this is decreasing, but this behavior would be pretty different from this behavior here. Okay, so we still need some more tools in order to find out more informations about the given function. In particular, we want to find out, okay, whether here at the beginning the function is like this here, or maybe doing something like this here. Okay, and for this we need a second derivative. Okay, so the next question we have to ask ourselves is, what does the second derivative tell us about the original function? We already saw, okay, that from the first derivative easy information of the first derivative, we can conclude to the original function. Now, for the second derivative, okay, so we saw that if we look at the increasing function, there are actually two different behaviors of increasing which are pretty different. So this is the first one. Okay, and this would be the second one. Okay, both functions are increasing. So this is a function. Both functions are increasing, but the behavior is somehow different. Now, what is the difference? Here, if you look at any point and consider the tangent to the function at this point here, so for instance at this point, no matter which point you choose, you see that the graph is always above the tangent. And if you do the same here, since you choose this point here, you see that the different behavior, okay, is reflected by that here the graph is below the tangent. No matter how you choose the point and the tangent, the graph is always below. And here, no matter how you choose the point and the tangent, the graph is always above. And that's essentially the difference between those two functions. And you have maybe learned in high school that this function is called concave upward, and this function here is called concave downward. Okay, so the definition of a concave upward function is at all points, the tangent lies below the function, and the definition of a function which is concave downward is just the opposite. Now, sometimes you also see in literature, sometimes this is called convex and this is called concave. This is just the same, but I think to use concave upward and concave downward is better because it immediately describes the essential behavior. Okay, so we have in our textbook, you find the definition. F is called concave upward on an interval if for all points in I, the tangent of 2 f at A is below f. Okay, similar, you have concave. So here, this is the important word. Similar, you have concave downward. Okay, and the next question is, okay, how to figure out where is a function, on which intervals is a function concave upward, on which interval is the function concave downward for a given function. Now, you see already that another way to describe concave upward is, if you look at the tangent, the slope of the tangent, okay, the slope of the tangent is increasing. Okay, so in other words, if you, because the slope of the tangent is given by the first derivative, okay, so the first derivative should be increasing, or in other words, the second derivative is larger than 0. So from the second derivative, you should be able to conclude whether a function is concave upward or concave downward. So if the second derivative is larger than 0, then the function should be concave upward. If the second derivative is smaller than 0, then the function is concave downward. This is not a proof, because I just told you that, because the definition actually does not immediately tell you that for a function which is concave upward, the first derivative is increasing. You cannot see this immediately from the definition. But of course, if you plot some examples, you can see this from examples. So we have a similar test as we have seen last time in order to figure out monotonic behavior for concavity behavior, namely if the second derivative is larger than 0 or smaller than 0, then the function is concave upward or concave downward, respectively. This is called in our textbook concavity test. Okay, so first, if second derivative is larger than 0 on an interval I, then f is concave upward on I, and similar if the function is if the second derivative is smaller than 0, then f is concave downward on I. Okay, so maybe let's look at the proof. I roughly explained already why this result is true. Okay, so if we choose a point a in I, what do we have to prove? We have to prove that the function f of x, okay, is always is for all x, the function is above the tangent. So what we have to prove is this here. But this should hold for all x not equal to a. Okay. Now, we saw last time already a good method how to prove such inequalities, namely the racetrack principle. Actually, we can also use the racetrack principle here. Okay, so we have two functions, f of x, and this is our function g of x. Okay, and we have a function f of x. Of course, it's easy that those functions satisfy the assumptions of the racetrack principle. Also observe that g of a is equal to f of a. Okay, so we start at the same position. So what we have to prove is that the derivative of f of x, okay, is always larger than the derivative of this function here. So this is what we have to prove. And then by the racetrack principle, so the racetrack principle tells us that, okay, if you have two functions, okay, you can consider them as the position of two horses. Okay, they start at the same point. Okay, and the velocity of the first horse is always larger than the velocity of the second horse. Okay, then you should get this here. Okay. So what we have to prove is this here. Okay, but in order to prove this, we use just the racetrack. So actually, last time I stated a little bit different. I had here larger equal, and then I get here also larger equal. Okay, but of course, if you have here larger, you get the same conclusion just with larger. Okay, so what I have to prove is this here. Okay, but here I can use again the racetrack principle now for applied to the function g of x, which is this constant here, and the function f of x, which is replaced by the first derivative of the function. Okay. Okay, so if I look at the function, call it f1 of x, which I define to be the derivative of this function, okay, and the function g1 of x, which I define to be this constant here. Okay, now again, so those are our two horses. Okay, you obviously see that f1 of a is equal to g1 of a. Okay, and you see that if you take the derivative of this function, what you get is the second derivative. Okay, and by definition, the second derivative is larger than the second derivative of this, than the first derivative of this function, which is 0. Okay, so here this is by definition. So I get from here that f1 of x is indeed larger than g1 of x if x is not equal to a. Okay, and this just means this here. Okay. So defining f1 at g1 like this, the assumptions are satisfied of the horse-track principle. I get this inequality, and then defining once more two functions gx and f of x, okay, like this here. Again, the assumptions of the racetrack principle are satisfied, and I get what I want to prove. Okay, so this is just the same as we have seen already last time. Okay, so any questions? So actually, you take derivatives, okay? You start from here. You want to prove something like this here. You define two functions. Okay, you see that you take derivatives. You have to prove this. If you cannot prove it, you take once more derivatives. Okay? And then you conclude back. Then you go from here to here. Okay? It's kind of, you always check. So you have to check, okay, that this is satisfied. In order to check this, you take once more derivative. But this is satisfied. Okay, now you can conclude back. Now, another definition, which you have seen in high school as well, assume that f is continuous at C. Now, C is called the inflection point. Okay, so inflection point. If the concavity behavior changes, so either from concave upward to concave downward, or from concave downward to concave upward. So we have a change in the concavity behavior at C. This is so-called inflection point. You have considered such points also in high school. Now, a first simple remark is that if f is differentiable at C, so if the tangent exists at C, then of course the function has to cross the tangent at an inflection point. Okay, why is this so? So if you have a tangent at the inflection point, the function has to cross the tangent. This is clear because the function, for instance, the concavity behavior is changing from concave upward to concave downward, but concave upward means that the function is above the function. Concave downward means that the function is below the function, is below the tangent. Okay, so if the tangent exists at the inflection point, of course the function must cross the tangent. Okay, because this behavior, whether the tangent is above the function or below the function is changing. Now that's the first thing. The second thing is actually you have something like similar to Fermat's theorem, also for inflection points. So you have something like assume that the second derivative exists near to close to a for x close to a. Close to c. Okay, so assume that the second derivative exists for x close to c. Moreover, assume that f has an inflection point at c, then the second derivative at c must be equal to 0. Okay, so this is actually similar to Fermat's theorem. So Fermat's theorem told us that by Fermat's theorem, if we have a local extrema at some point c, and the derivative exists at c, then the derivative must be equal to 0. And you have something which similar for inflection points. So if the second derivative exists for x close to c, and if c indeed is an inflection point, then the second derivative must be equal to 0. Okay, the proof of this result is you just look at the first derivative. Okay, so proof. Okay. Consider the first derivative. Okay, now we know that if you apply the first derivative test, okay, then we know that so if you apply the first derivative test, because you see that the second derivative changes sign at c, okay, so we can apply the first derivative test and get that the first derivative has at c a local extreme value, and now we apply Fermat's theorem. Okay, so we know that the first derivative, okay, has a local extreme value at c. And we know that the derivative of the first derivative exists at c. Okay, so the derivative at c must be equal to 0. So you see that this result follows actually from the first derivative test and from Fermat's theorem, just by carefully applying both. Okay, so actually you apply the first derivative test onto the function onto the first derivative. Okay, then you get that you have a local extrema there, and from the local extrema and the existence of the second derivative at c, you get that the second derivative at c must be equal to 0. Okay, so this is sometimes helpful in order to find inflection points, because from here you see that okay, so if the second derivative exists everywhere, then you just have to equate it to 0, and you find possible candidates of inflection points. But the inverse is not necessarily true, which is a similar situation as in Fermat's theorem. You know that if you find a point where the first derivative is equal to 0, it's not necessary that the function has an extreme value at this point. And the same is true here for this result here. So the inverse does not necessarily hold. If you have a point c where the second derivative is equal to 0, it's not necessary that you have an inflection point here. You just have to think about x to the 4. Okay, so if you look at x to the 4, at x is equal to 0, you get that the second derivative is equal to 0. But if you look at the graph, the concavity behavior of the graph is not changing, so you do not have an inflection point at c. Okay, but inflection points, we had something similar to the first derivative test, namely, if a function is continuous at a point C, and the second derivative changes the sign, okay, then we know from the concavity test that we must have an inflection point at C. So just from the definition, we know we have already something like the first derivative test for the for inflection points, but it involves the second derivative actually. Okay, but it's the same test just for inflection points. So we see that if we want to understand the monotonicity behavior of a function, we will look at the first derivative. Then we normally will find intervals of increase and decrease. From those intervals, we can immediately conclude where are the local extremas. Then we will compute the second derivative. We will find the intervals of where the function is concave upward and where the function is concave downward. And then from the definition of inflection points, we also know where the inflection points are. So we do this all as one procedure. Now, you might have learned another result in high school in order to figure out whether at some point C the function has an extreme value or not, which our textbook calls the second derivative test. Okay, so the second derivative test is once more in order to figure out whether or not at a given critical point a function has a local extrema. Now, we have seen already one test which solves this task, namely the first derivative test. For the second derivative test, we have the assumption, so assume that the second derivative is continuous close for x close to C, sufficiently close to C. Now, if the first derivative at C is equal to 0, okay, so this means that C is a critical point, and the second derivative at C is larger than 0, then I guess you have learned in high school that f has a local minimum at C. And if the derivative of f at C is equal to 0 and the second derivative is okay, then by replacing f by minus f, it's clear that f must have a local maximum at C. Okay, we will discuss the situation where the second derivative is equal to 0 in a few minutes. So first, let's prove this result here. I guess most of you have seen this in high school. Now, for us, this test is not so important. For us, more important is, at this moment, is the first derivative test. Because anyway, we have, normally, if we want to figure out how the graph of a function looks like, we will first compute the first derivative and then the second derivative. And we will also, while computing the first derivative, after computing the first derivative, we will find out, okay, where's the function increasing, decreasing. And then we know everything about the local extreme values, and we do not need the second derivative test because we can conclude it already from the sign change of the first derivative. Also, the second and the first derivative test solve the same task. They are quite different because you see that here the assumptions are much stronger. Okay, the test we saw last time, okay, has the only assumption which the test last time has is that f must be continuous at C, and that's it. Here you need that the second derivative not only exists but is also continuous for all x close to C. So these are pretty strong assumptions, okay? But it's much more convenient using this test in order to figure out whether you have a local extrema at some point or not, because you just have to plug in, you look at the sign. So this is much more easier in some sense than the first derivative test, okay? But the second derivative test has another disadvantage, namely, in case where the second derivative is equal to 0, normally no conclusion, okay, unless you look at higher derivatives. For instance, last time I told you that you can use the first derivative test in order to check the function f of x is equal to the absolute value of x. But you cannot use this test here because if you have absolute value of x, then not even the first derivative exists. So you do not have existence of the second derivative. Okay, so I guess most of you have seen this test in high school. Maybe no proof in high school. Maybe also no assumptions in high school. Because here this assumption is important. The second derivative is continuous. You have to. I should remark that it's different to assume that the second derivative just exists, or the second derivative is continuous. It's pretty different because we have seen already that, of course, it's not every function which is differentiable has the property that the derivative is automatically continuous. Okay, these are different properties. Now, why do I need continuous here? Because, for instance, if you look at the proof of the first part, okay, so we have this assumption here that the derivative of second derivative of f at c is larger than 0. And now this is pretty important. Okay, so because we know that the second derivative is continuous, we know that this inequality will still hold if you are close to c. Okay, so the second derivative will be larger than 0 for x sufficiently close to. So you should notice, okay, what I use here, okay, is already this assumption. Okay, because I know that the function is continuous, the second derivative is continuous, and I know larger than 0. So this property certainly is still valid locally around C. Okay, so I get this here. But now I can apply the concavity test. So now I can, from the concavity test, I can conclude that f is concave upward. Again, for all x close to C. Okay, but this means, so what I mean here for x close to C is there exists the interval around C, containing C, where the function is concave upward. Okay, but concave upward means that we are above, so the function is above the tangent. Okay, but the tangent, you see, is horizontal. Okay, so from here it follows that f is above the horizontal tangent at C. Okay, but this clearly means that I have a local minimum there. Okay, so you should, of course, something like this here, you could argue also by looking at the graph. Okay, but you should realize that I do not use here anything in this direction. Okay, so already from the concavity test, I can conclude that I must have a local minimum at C. And the same for the second part. But as I said, for the second part, actually, you can use either the same reasoning or you can replace the original function by minus f. Okay, so any questions to this? Any questions? Now, maybe you have learned in high school as well what happens if the second derivative is equal to 0 as well, where this test doesn't give any answer now. So let's assume that the third derivative is continuous for all x close to C, okay, and assume that the first derivative and the second derivative both are equal to 0. Okay, and assume that the third derivative is not equal to 0. Okay. Then, so what can we conclude in this case? So you see that if we look at the function f, at the derivative of the function, okay, the derivative of the function satisfies all the assumptions of the second. So this is not the second derivative test here, so I should maybe erase this just that it doesn't get too confusing. Okay, so if I have these assumptions here, okay, those assumptions, I can look at the first derivative of this function, and the first derivative of this function, so this, call this a new function, g will satisfy the properties of the assumptions of the second derivative test. So we will apply the second derivative test onto the first derivative of f. Okay, and you see the assumptions are satisfied because the second derivative of g is continuous for x close to c because it's the third derivative. You see that that the first derivative at c is equal to 0, and the second derivative at the first derivative of g is equal to 0, and the second derivative of g not equal to 0. So either larger than 0 or smaller than 0. So from the first derivative test, from the second derivative test, okay, we get that g has a local extrema at c. Okay, so but you see that g at c is equal to 0. Okay, so you just have two choices. So if this is c here, you just have actually two choices for the first derivative, namely either or this. Okay. But now you can apply the first derivative test. So if you now apply the first derivative test, you see that it's impossible that our function has a local extrema at c. Okay. So by the first derivative test, f has no local extrema f does not have a local extrema at c. Okay, so in this case, I can conclude that f has no local extrema Okay, so you have to consider the proof. The proof uses both the second derivative test and the first derivative test. So once I have proved the second derivative test, okay, I can discuss the case here, okay, by using the second derivative test and the first derivative test. Okay, the second derivative test gives us a local extrema for the derivative, okay, and then because the derivative at c is equal to 0, okay, so we have only those two. So you see that this first derivative does not have a sign change. And then you can use the first derivative test in order to conclude that f has no local extrema at c. So normally I like to give such examples for homework because there are always some students who try to argue just by using a graph. Okay, but actually we have proved all the tools, okay, without referring to a picture, and it's quite nice to prove something like this here because it involves exactly the ideas we have seen before. You see also that so how about so there is no local extrema at c. How about the question whether there is an inflection point at c? Okay, you can think about how to argue. So does f does f have an inflection point at c? Try to find a reason which does not uses a picture. Okay, try to find the argument which doesn't make use of a picture. Okay, so how do you argue? Again, under this assumption, okay, you know that the third derivative, for instance, is smaller than 0 at c. So actually, you can choose. You can use two cases. So case 1, the third derivative at c is smaller than 0. But I assume that the third derivative is continuous. Okay, for all x close to c. So I can conclude from this assumption here that this property here will remain true if x is close to c. Okay, so this will still hold for all x close to c. Okay, but now this means from the increasing decreasing test, I know now that the function is decreasing. Okay, so the second derivative is decreasing. Okay. But this means I have a sign change. Because the second derivative at c is equal to 0, so this means I certainly have a sign change, okay, from positive to negative. Okay, so from this property I see that the sign of the second derivative is changing. Okay, but this means by definition that f has an inflection point. And of course, the case 2 is the same. I just get here increasing. Okay? So whenever you have an exercise like this as your homework, okay, you should argue very carefully, step by step. Okay? And the best thing is you do not refer to any picture. I know that freshmen have some problems in order to do this in a systematic way. And normally, if I give such an exercise, it's very complicated for my TAs to grade it, because some students might have the right idea, but they do not write it down carefully. So we cannot see, okay, how do you conclude from one step to the next one? Okay, so in our textbook, you'll find a couple of such exercises, and it's worth it to spend some time in order to solve them, just that you learn to argue here in such cases systematically. So for the case 2, similarly. Okay, so you see that this is the case which is not discussed in our textbook. If you look at the formulation of the second derivative test, so if the second derivative is 0 as well, you have to look at the third derivative. Now, of course, the next question is, okay, well, how about the case where the third derivative is 0 as well? Okay, you can you use a similar way. You argue similarly. Okay, you can find the similar results for the case where more derivatives than just the first, second, and third are equal to 0. Okay. Let's maybe look at one example, because now we can already do quite a lot, because we know already now quite a lot of results how to conclude from derivatives about the original function. Now, for instance, if you have given such a result here, normally the test case, okay, find the intervals of increase, decrease, find local extrema, find the intervals of where the function is concave upward, where the function is concave downward, and find the inflection points. So normally an example typically looks like this here. So you see that for this example, first we have to compute the first derivative. Okay, so you have x squared minus 1 squared. Now you have 2x. Then minus 2x to the cube. Okay, so you have minus 2x. over x squared minus 1 square. So you see that, first of all, the function is not defined as minus 1 and 1. And you see, if you look at the derivative, then because this here will always be larger or equal than 0. So you see, if x is smaller than 0, then the function is increasing. If x is larger than 0, the function is decreasing. So if x is larger than 0 or smaller than 0, f is increasing. And if x is larger than 0, then f is decreasing. Okay, so that's normally the first thing to do. You figure out, okay, the intervals where the function is increasing and decreasing. Now, the second thing is to look at, once you understand this behavior, it's quite easy to discuss local extremas, local extreme values. So you see that the function is differentiable everywhere where the function is defined. The only critical point is x is equal to 0. But from here we know already that at x is equal to 0 we have a absolute maximum, local maximum. So the only critical point is 0. And from the first derivative test, we see we have a local maximum. Okay, so this is the first thing. This is actually what you can see from the first derivative. You can understand the monotonic behavior of the function, and you can find you can discuss local extreme values. Now, if we look at the second derivative. Okay, now it's getting more tedious. Okay, then minus 2 x squared minus 1 square minus okay, so now we have to simplify this, so we can erase here 1x squared minus 1, then things are getting a little bit easier. Then we have minus 2x squared plus 2 plus 8x squared. Okay, so what we get is 6x squared plus 2 over x squared minus 1 to the cube. Okay, and you see that the numerator always larger than 0. Okay, so you just have to look at the denominator, and you see if the absolute value of x is larger than 1, then what you get is here something positive, which means concave upward. And if the absolute value of x is smaller than 1, then you get here something which is negative, which means concave downward. Okay, so as for the concavity behavior, okay, so if the absolute value of x is larger than 1, then we have concave upward. And if the absolute value of x is smaller than 1, then we have concave downward. Okay, so this already tells us quite a lot of this is already quite a lot of information about the function. But you see, obviously, important other information if you want to plot the graph of the function are horizontal and vertical asymptotes. Okay, so you see that if you consider the limit as x tends to plus minus infinity, okay, of the function f of x, what you will get is equal to 1. And if you look at the limit x tends to, let's say, 1 plus of x squared over x minus 1, x plus 1. Okay, so if you look at this here, you see it's always positive, so what you get is plus infinity. And similar, if you look at the limit x tends to 1 minus of x squared over x minus 1, x plus 1, then you get minus infinity. And actually, I do not have to consider negative x here because you see that the function is symmetric about the y-axis. Okay, you see that f of x is equal to f of minus x, which means when I understand the function for positive x, I understand it for negative x as well, just by reflecting. And from this information, I can now already plot the graph. Okay, you see from here that 1 is a horizontal asymptote. You see that plus minus 1 are vertical asymptotes. So this is normally the first information we are going to plot. Okay, so we have here minus 1. We have here plus 1. Okay, so we see that if x tends to 1 from the right, okay, we are going to plus infinity, and we see that and we know that the function here is always decreasing, so it must look like this here. We have here the horizontal asymptote. Moreover, we know there is no inflection point here, and the function is concave upward. So it will look here. It will look like this here. Okay, and here it will look like this as well. And here we have this behavior. Okay, so you see that this is actually enough information in order to plot the graph of a function. So normally, what you have to do first is normally the first thing is you have to find the domain of the function. Okay, then it pays off to discuss symmetry. Okay, so if you, for instance, can figure out that the function is an even function, then this just means you just have to discuss x is larger or equal than 0, and then just reflect about the y-axis. Then asymptotes is very important, and this is something which actually a graphing device like Maple is not able to handle because your viewing rectangle will always be restricted. So horizontal and vertical asymptotes are important. And then what we normally do is we compute the first derivative. We look at, from the first derivative, we look at sign changes. So we try to figure out where's the function increasing, decreasing. We use this information then together with the first derivative test in order to find the local extreme values. Then we compute the second derivative. We look at the sign change in order to find the intervals where the function is concave upward and concave downward. And we use this information then in order to discuss inflection points. And finally, we plot the graph. And what we need as well is our other helpful informations are zeros. So where's the function equal to 0, which are the x-intercepts. And normally, in order to understand the shift, because you have to understand whether this is shifted up or not, you have also to find the y-intercept, which explains you where is the function located. And those information, because we will later on discuss this, there is one section in our textbook discusses this in a more systematic manner, but the information which I mentioned is normally the information we gather in order to figure out how a given function, how the graph of a given function looks like, and then we plot it. And the only important thing is, so later on you find a section in our textbook, I think section 4.5, which is dedicated to such a topic. The only important thing is that you learn to do this in a systematic way. So it's good to have always. You don't necessarily have to follow the order in the textbook, but it's good to have a fixed order and do it always in the same order, just to do it systematically, that you do not forget any of the information. In section 4.5, there is a step-by-step program how to proceed if you want to find the graph of a function. But as I said, you do not necessarily have to do it in the same order as the author. But some things you have to compute first if you want to compute. If you want to understand inflection points, obviously you have to compute the second derivative and so on. So it's quite obvious. how to do this. But of course, you can change it a little bit to order this. Doesn't matter. Now, as we have seen here already for this example, very important information about the function is given by horizontal and vertical asymptotes. This is horizontal asymptotes are in particular important because this is something Maple cannot find, because your viewing rectangle will be or a graphing device. If you use a graphing device in order to understand how a function looks like, it might be complicated to. It is not possible to understand how does the function behave if x is getting very large or very small. So, which is normally captured by horizontal asymptotes. This is important information. And also vertical asymptotes, the graphing devices normally have problems if a function is not defined. Like this function here, x squared over x squared minus 1 is not defined as x is equal to 1 and x is equal to minus 1. And Maple has big problems in order to plot such functions around two values where the function is not defined. So this is something where it pays off to use calculus in order to understand how a graph looks like. So a graphing device normally alone is not enough in order to understand the graph of a given function. You also have to the best thing is you also do some calculus and you use the graphing device. So you guide the graphing device how to plot the graphs is the best thing in order to understand essential properties of functions. Now, in order to compute horizontal asymptotes and vertical asymptotes, we have to compute limits. This is something we have already discussed in chapter 3, but we are still lacking one important tool, namely the rules of the L'Hopital, which we are going to learn next. Not sure whether it's L or LE. L is enough. Okay, so you have learned them maybe in high school, but you have not seen the proof, and maybe I can tell you some things which you haven't, which was not emphasized in high school. So what we want to do is for instance, we want to find a limit like this one. Many limits we can compute, but for instance, if we have to compute a limit like this one, we do not have any tools yet in order to figure out, okay, what is the limit? Actually, it's not really true, because you could say, okay, it's the derivative, okay? Because you see that, okay, so this is the, by definition, okay, this is the derivative of the function ln of x at x is equal to 1, okay, you can use this. But actually, this limit, okay, when we discussed the derivative of the logarithm, okay, we haven't proved, okay, that the limit is, we have assumed that the limit exists, okay, but we haven't obtained it. Now, so for this limit, the special thing is that if you try to apply the quotient rule, then you see that you end up with something which is 0 over 0. Okay, and it essentially depends. So you can think about as x tends to 1, this is tending to 0 here, and as x tends to 1, this function is also tending to 0, and it depends which function tends to 0 faster, okay, or which function does tend to 0 slower, okay, and this function normally will decide the behavior. Okay, so we have something like this here, and this is normally called the indeterminate form. So this is an indeterminate form of type 0, 0. So this is called indeterminate. No, not indeterminate, indeterminate, sorry. Because we cannot determinate it, so that's why it's called indeterminate. We cannot determinate it. And you can easily find examples, okay, where indeed you have 0 over 0, so you encounter indeterminate form of type 0 over 0, but you get any possible value for 0 over 0. So indeed, this is really an indeterminate form as is shown by several examples. We saw some special cases where we could handle indeterminate form of 0 over 0, but we used tricks for this. So we saw that, for instance, if you have the limit x tends to 1, x minus 1 over x squared minus 1. Okay, so in this case, you write the denominator, you write the denominator as x minus 1 times x plus 1, and now you can erase the bad guy, the guy which is responsible for the behavior 0 over 0, namely this one here. Okay, and if you do this, then in fact you can use the limit laws and you get 1/2. This here seems to be trivial. You have seen this in high school, and actually the proof or the reason why the reason behind the rules of the L'Hopital is exactly this. Actually, we do the same, but on a more abstract level. Okay, so this here, this way in order to handle something like this, you erase the bad guy. Okay, it's the idea behind the rules of the L'Hopital. We will see this in a minute. Now, there are also other indeterminate forms, like if you look at the same function, but the limit x tends to infinity of ln x over x minus 1. So also here you get something which you cannot determinate, infinity over infinity. So this can take on any value depending on the two functions. Here, the essential thing is, okay, which function does grow faster as x tends to infinity? This function tends to infinity as x grows to infinity. It grows to infinity, and this function as well. The only question is which one will tend to infinity faster. And we saw already that actually the ln of x is tending to infinity slower than any power function. So from this, you can guess already that the limit is equal to 0. Okay, but this is not a proof here. And also for such indeterminate forms, we saw examples where we could use tricks in order to handle them. For instance, x squared plus 1 over 3x squared minus 1. Okay, so our trick which we used is a little bit of the same flavor. So we divided numerator and denominator by 1 over x squared and got 1 plus 1 over x squared over 3 minus 1 over x squared. And so it's kind of the same idea. We try to cancel out. We try to cancel the bad guy. And now you can use the quotient rule, and you get 1 over 3. Now, okay, so let's state the rules of the L'Hopital, and then discuss them. You have already learned in high school that actually the way to handle something like this here, the best way to handle this, or the most systematic way to handle this, is taking derivatives of numerator and denominator, and considering the limit after you took derivatives. Now in high school, maybe there was no reason. Someone told you this rule or this theorem, or told you, okay, you can do it like this. And this is maybe this is something which you might think is rather strange. Okay, why I'm allowed to take derivatives here, and then if I take the limit, okay, and the limit exists, okay, it will be equal to the original limit. Now the reason behind this rule is actually pretty simple, and here is already the main idea in order to prove it. But let's first state the theorem. Okay, so there are assumptions. Assume that the derivative of f and the derivative of g exist, and the derivative of g is not equal to 0. So maybe I should add here x for all x close to a. Okay, but as always, if we consider limits, okay, it's not necessary that those assumptions must be satisfied at a itself. Okay, for instance, the original function maybe are not even defined at a. Okay, assume that I just discussed this case here. The limit of f of x as x tends to a is equal to the limit of g of x as x tends to a is equal to 0. So I just discussed the case 0 over 0. The case infinity over infinity is handled in the same manner. Then the limit of f of x over g of x as x tends to a is equal to the limit if the latter limit, if this limit here exists or is equal to plus minus infinity. Okay, so also in this case where this limit is equal to plus minus infinity, okay, this holds. Now, the most important thing which you might not have discussed in high school is that you have assumptions here and the assumptions must be satisfied. Otherwise, the result you get might be wrong. Okay, so the assumptions essentially which you have here is this assumption. Okay, so you really have an indeterminate form of type 0 over 0. If you do not have an indeterminate form and you do this, okay, the limits might be different. Okay, so you have to check first this here. And this is important as well. You have to check whether this limit exists or not. And existence here includes the case plus minus infinity. If this limit does not exist, you cannot conclude that this limit does not exist. You have to do it completely different. Okay, so you have to be careful when to apply the rules of the L'Hopital. Namely, all the assumptions must be satisfied. Now, before proving this result, this is not possible today. But the first thing I want to do is I want to just make you understand why this result is true. Okay, so you might maybe think it's quite mysterious, okay, that you can do it like this here, that you can replace the functions here by the derivatives, take the limit, and it's equal. Okay, but actually the reason is pretty easy. Namely, you can roughly think about the situation as follows. So we have here our two functions, f and g. So this is f here, and we have a function g. Okay, and both at a we assume they are equal to 0. So this point here is a. Now, this is not really a function what I plot here. Okay, so you see that you have here two tangents. So you have this tangent and this tangent. Okay, so we assume, because we assume that this is f of x and this is g of x. Okay, so we assume this here. Of course, it's not necessary that the function f and g, okay, must are defined at a. Okay, it's not necessary. This is not necessary here. Okay, so maybe the function f and g look much more complicated. Okay, here this is the simplified version where the simplified situation where actually the derivatives are also continuous and so on. Okay, but let's maybe look at this picture in order to motivate the result. Now, what we want to do is we want to compute the limit as x tends to a of f of x over g of x. Okay. Now, what do we observe as x is closing into a? If x is getting closer and closer to a, okay, I can replace the original function by the tangents because roughly because the tangents should approximate very well. If x is very close to a, the tangent should approximate very well the original function. Okay. So if you, in other words, if you choose a smaller viewing rectangle here in a graphing device, okay, it should hold that what you see actually are just two lines. Okay, so you can replace f of x, okay, by the tangent to f at a, okay, which is given by actually plus f of a, but f of a is equal to 0, okay, over okay. And now you see the main idea. The main idea is just the same as we have used already in high school for rational functions. Namely, you just cancel the bad guy. Okay, and what remains is the derivative of f over a, the derivative of f at a over the derivative of g at a. But since this is a constant, okay, the limit is just equal to this constant, or you can also replace the a here again by x. Okay, so you see that actually this rule is easily explained if the functions here are smooth enough. And indeed, if the derivatives both are continuous, okay, and the derivative of g at a is not equal to 0, in this special case, the proof is trivial. It's very easy, namely. So are there any questions to this? This is maybe the most important picture. Okay, you should understand this, because this helps you to understand why this rule is true, why this rule holds. So this is the basic idea also behind the proof. Now, as I said, if you assume that the derivatives are continuous, not only for x close to a, but also at a, and g of a is not, the derivative of g of a is not equal to 0. Okay, so in this case, under these assumptions, the proof of the result is much more easy. So we look at the derivatives, okay, because they are continuous, and you have this here, so you can evaluate. You can use the limit laws, so you can evaluate this as the derivative of f at a over the derivative of g at a. Okay, now you just plug in the definition of the derivatives. So you have, this is the limit, f of x minus f of a over x minus a as x tends to a over, and here you have the limit x tends to a, g of x minus g of a over x minus a. Okay, but if the derivatives are continuous, f and g are continuous as well, so f of a, you can compute this limit by plugging in. So f of a is equal to 0, g of a is equal to 0. Okay, so you see that those here are equal to 0. So what you get is, you can take out the limits, and the rest is f of x over g of x. Okay, so if you assume, in addition to those assumptions, that the derivatives do exist but are also continuous, okay, and the derivative so everywhere, not only for x close to a, also at a, and the derivative of g at a is not equal to 0, then the proof is trivial. Next time we will see how to prove the result, because you see that these assumptions here are best possible, okay, because this is certainly something which you need in order to take derivatives, okay, and you need that this is satisfied here, otherwise you cannot consider this fraction here. So you see that this assumption here are best possible, okay, and weaker, much weaker than those assumptions. And we will see, indeed, if you want to prove the result under this more general assumptions, the proof is more complicated, much more complicated than if you just look at this special case, which is more or less an exercise. And this we are going to do next time. So are there any questions? Okay, so the most important thing you should understand is this intuition which is in our textbook and which I showed you here, namely that actually what is behind this result is just canceling the bad guy. It's more or less the same method we have used already for a long time in order to handle rational functions. Okay, so this is the main idea behind this result.